So in this lecture we're going to solve a very simple example of reserve estimation, but using the Monte Carlo method, considering uncertainty. So what we have is a reserve estimation, and estimates of reserves are needed for in early phases of field development. Also, when you deliver the PDO, you are required to deliver an estimation, probability, a PDF and a CDF of the reserves. These are actually included in the field development plan of Energian. As a porosity, but then we had one section where we had for example here, we have initial, in this case it's not reserves, but it's actually what we have in the subsurface. So we're going to see an example. How do we calculate this graph? Reserve estimation, and we have a case is an undersaturated oil reservoir. We see first the equation that we are going to use. Okay, so we have that a NPU. Okay, this is the total recoverable reserves. Okay, or is the ultimate cumulative production? It is the same. This is equal to the rock volume times a use a dot, okay, times a that's the bulk rock volume multiplied by the porosity. That gives me how much a pore volume I have. Then I have something called net to gross, which is how much of is the ratio, because in the, for example, if you do logging in a layer, okay, you might have, this is the hydrocarbon, the bearing layer, and then you might have some shale layers in between in the reservoir. So actually the net to gross ratio will be something like the sum of all of these the ones that are not dirty, in a simplified way, okay? All of them that are H1 plus H2 plus H3 plus H4 divided by H total. Considering the ones that are hydrocarbon bearing layers, not the ones that cannot have hydrocarbons. Okay, so you have, this gives you actually the pore volume, and then you have the oil saturation, because you want to know, usually we have, for example, if it's an undersaturated oil reservoir, we have a connate water that is occupying part of the pore. We look at the pore space. Okay, we have typically some water, connate water, which is if the rock is hydrophilic, so then it's on the rock, and then you have some oil that is essentially there. Okay, and then I have this gives me volume of oil at local conditions, then I have to divide by BO to obtain at standard conditions, and finally I need to know the recovery factor. And let's call it ultimate recovery factor. So we're going to calculate. You see, you have the TRR, which is a calculation. Okay, is simply this equation. And we have all of these input parameters that are highly uncertain. Okay, all of them are highly uncertain, and especially the ultimate recovery factor. Okay, some of them are of geological origin, some of them are fluid. This BO is due to fluid properties, and then finally end up with the NPU. So we want to perform a Monte Carlo simulation to determine the distribution of this NPU. So for that, I provided you with an Excel sheet. That you can use. Okay, where you see first you have all the parameters that we mentioned: rock volume, porosity, net to gross, oil saturation, volume, oil volume factor, and recovery factor, and then finally you have the NPU. And you see the distribution that each one of them is characterized, so all of them are uniform distribution, almost all of them. So you have here mean and max, porosity, mean and max, net to gross also uniform. We don't have at this stage, we don't have any other information, we don't have any exploration wells, maybe we have some seismic. So we have these, all of them are uniform. But however, in the recovery factor, the ultimate recovery factor, we see that we have minimum and the maximum, but actually we also have a mode. So the recovery factor is, let's put it here on the notes. So BR, viscosity, porosity, net to gross, SO and BO have a uniform distribution, PDF. Okay, so that means that all of them have something, a situation like that, while the ultimate recovery factor has a triangular distribution in which it's something like this. Okay, you have a mode, and you have a max, and you have a min. That means that you can have some extreme cases where you have high recovery factor or low recovery factor, but then you have one recovery factor which is the most likely. And this distribution, you already covered it in the quiz, but maybe we can see how it looks like. It's an analytical distribution in which okay, like this is the expression of the PDF, and you have the expression of the CDF. Okay, so let's go back to our Excel sheet. So the first thing we have to make, remember, is number of iterations. So let's say we want to make 1,000 iterations. Okay, or let's say 500, not to make them that many. So if we want to populate that for 500, okay, just to have the number of the iterations. So for that I can use series, okay, and I want to fill in a column, and I want to start with 1 and stop with 100, with 500. Yeah, and then I have all my 500 rows. Okay, so if you now remember what is this, the second step I have to make in Monte Carlo. So I had to come to the CDF, okay, the CDF, and how is the CDF of this uniform PDF going to look like? So it's going to look something like that. The integral of a constant is simply a straight line. Okay, and here I have my mean, and here I have my max. I have to come to that straight line and read that value. Okay, and this value has to be random. That's what Monte Carlo is doing. I come with a random number, I enter into the CDF, and then I read this value of the value. Okay, it's, for example, porosity. So I have already programmed that for you. I made your life easy. So let's see the function. X uniform, that's going to give me the value of the variable uniform. Okay, with a uniform distribution, you just have to give the A and the B. A is the minimum, B is the maximum. Okay, and first, what it's doing is pulling out a random number, and for this to work properly you have to use volatile this sentence, which is simply saying please refresh and generate a random number, because if not, sometimes it might be that the number is not random, it becomes frozen after some time. Okay, so this is saying always generate a random number. You generate a random number, and then this is the equation of the straight line. With that random number, you come to this slope, this is the y, and then you read the value in the x. So let's apply that equation for all x uniform. Okay, you need the minimum, and then you need also the maximum. That's going to spit a random value in the interval using but I don't want, when I pull it down, I don't want it to change the row. I want it to change the column when I pull it to the right, but not down. So then I'm going to freeze the number, okay, such that when I pull it down, actually you see it's not going to change. Okay, but when I pull it to the right, it's actually changing. Okay, and these numbers I should actually make it a bit nicer, scientific. This one should have less decimal points. These also are kind of fractions, so let's reduce number of decimal points here. Yeah, and all of these are going to be calculated, so they should be in blue. Okay, and if you, for example, you make any change on the sheet, for example, you see I automatically get a new value, because what is happening is that it's calling the function to be evaluated again if I make any change, and then everything is re-evaluated. This random number is again pulled back, is pulled, and then I get a new sample. Then NPU, here I simply calculate, is one iteration, so my simulation here is simply to perform that multiplication divided by BO, and I'm going to use this equation for that. So the equation is called NPU, and this NPU depends on the BO, depends on the FR, depends on the rock volume, porosity, the two gross, and SO. Yeah, and it tells me in this case this calculation is made in barrels, so it tells me that it's around 82 million. And this should also be in blue. Okay, then simply to make all my calculations and all my samples, I simply extend it down, and it's calculating, taking some time. Okay, and that's how simply I have all my samples, random samples, and I have the results 81, 89, etc. So now let's take these results, and we're going to do the analysis, the frequency analysis, on a separate sheet, because if I start making changes here, then all the time these samples are going to change and they're going to get updated. So that's not exactly what I want. I want simply to take these iterations and perform a frequency analysis on those iterations. I will paste it here. Okay, you see it's again calculating the sheet. So now I will have different values of what it had originally. Okay, I'm going to close. Okay, and I'm going to say, just do some formatting. Okay, and now I perform my frequency analysis. I say mean, max, and then number of beans and delta. Actually, maybe I should have one more. That will be, because it's a bit uncomfortable to work with so big numbers. So I will simply make one column which will be in million barrels. And I will simply divide this by 100. Sorry, by a million. and I will say this is a general number, and I will reduce simply half, and I'm going to apply this is rather to this column. Okay, just to avoid working with such a big number. And here it should be general. I reduce. Okay, number of beans. Let's say I want to work with I don't know, maybe 15 beans. And here the nx, they will be the max minus the mean divided by this n minus 1, right? Okay, so then I say the NPU values, it will be from the minimum, it will say the mean, the previous plus the delta, then I pull it down, go to 73. Okay, so here I have how many beans I have? 15 beans. Just change a bit the color, just to keep the convention of things. This is calculated, this is given, this is also NPU. We should put the units here. You can copy and paste. And here is we count how much we have, and we select first the data, this one, and the beans. Okay, close parentheses and then Control Shift Enter. And then I have the sum, how many I have. And then I calculate the relative frequency. This, let's call it probability, which will be this guy divided by this guy. Let's put 3, and then we say the cumulative CDF. Call this one the PDF and this one the CDF, and then we calculate the inverse CDF. Because for the inverse CDF we have a nice discussion. Okay, CDF will be this one, it will be this one plus this one, and then I pull it down, and then here it will be, actually I start from bottom up, so here will be this one, and here will be this one plus this one. Okay, and let's make the plots, which will take some time. Bar column is this one. The PDF, and then the labels are going to be these guys here, and this is going to move to a new sheet. This will be the PDF, and here I have to change this font size, is too small. Black, in bold, but let's put it here in black. Then let's add a line. And I have to put the axis titles. This will be probability, the PDF. This will be the NPU, or ultimate oil cumulative oil production in, and is NPU, and the units are 1 e to the 6. And I might put a solid line. I remove this other line, and finally I remove also the gap between these two. So that's how it looks like, and you see more or less you're getting an impression that is, well, looks like a normal distribution, but actually it's a bit tilted to the left. So in that case, this is a log normal distribution. Change this, let's call it data. Okay, now let's plot the CDF and the PDF. So let's create a using the same. In this case, we want to take the first we have to change the type of the chart. We want to use this one, and this is going to be D and F. Actually it's not F, but it's E, it's G. And we change this to we're going to change that to color black, and here we know that the maximum and minimum are 33 and 173, so change that to the axis will be from 30 to 180. Okay, and this one, I guess we can take out a few decimal points. We don't need so many. 2 only, or 1 only. Okay, this will be the cumulative probability. This will be the CDF, and then we have to duplicate this one and create the inverse CDF. And this one is going to go from a G and H. And we change the color, I'm not sure why. So those are the results, and you see with the Monte Carlo simulation we actually were able to quantify, to now compute a PDF and a CDF of the initial oil of the reserves. Okay, how much oil we can recover. This is inverse. Okay, it's actually, well, the 1 minus the cumulative. Okay, this chart is called the inverse CDF, but actually this is 1 minus the cumulative distribution. So one comment I have before we close this session, and you saw how it was done, is that this curve we as you show in the one of Karish and Tanin in the field development plan, we have to show it, but essentially people mainly work is with these numbers that you have here. Okay, so this curve is called the expectation curve. It's called the expectation curve. So companies, instead of working with this curve directly, instead of giving this curve, they typically work with for example, they call it here, I think they use a nomenclature here. Well, here they use P50. So instead of working with the whole curve, they work with a few values. So they work with the how we say, a conservative estimate, the average estimate, and they work also with I forgot the name, sorry, with the optimistic estimate. So for example, if we go here to one percentage that people use typically here is 90%, here they use 50%, and here they use 10%. So see here, and this is called the P90, the P50, and the P10. Okay, so for example, if you come here and you go enter with the P90 and you read down, okay, then you obtain that for example, this is 60, maybe this will be, for example, 65 million. Okay. That means that you can be 90% of the reserves, okay, are going to be equal to 65 e to the 6 or bigger. So it's a good number, it's a very conservative estimate, because if I make my calculations based on this number, actually saying that I'm very conservative, I'm saying still 90% of the cases are going to have that number or higher. When you go to P50, which is one that is typically used, okay, in this case, let's say we're close to 90, this is similar to close to 90. I'm saying that 50% of all cases that I simulated, they are actually higher or equal or higher than 90 million. Okay, 90 million. And then finally, the most optimistic estimate, which is 10%. Okay, and I can say this is 120, 125. This is roughly 125 e to the 6. This is telling me that actually only 10% of the cases are going to have, I will be able to recover 126 million barrels of oil or higher for only 10% of the cases. So this one, that's what I call the conservative estimate, the average estimate, and the optimistic estimate. And people use different names. Okay, sometimes they call it the best, the average, or they call it simply with these numbers, P90, P50, or P10, or sometimes they use different percentage. Okay, for some companies they use 60%, they use 80%, they use 20%. So there are different definitions how you define these numbers. But essentially, the idea is that instead of using this curve, okay, you simply pick 3 numbers with some percentages already predefined, and then I use these percentages to show the type of reserves I have, okay, or the initial value in place. That's it for today. Thank you for attending. Bye bye.